I see that Divesh is connected, so I would ask to show the presentation. I had received the video, but you are here, so please go ahead yourself.
So can you see my screen? And can you hear me?
It's coming up, yes, and we can hear you. Thank you.
Okay, just a second. I guess I have to start with this. Hello, everyone. I'm Devesh Jain, a graduate student in the National Center for Radio Astrophysics, India. Today, I'll be talking about the origin of a Radio Phoenix candidate in Abell 1914. This work was done under the supervision of Dr. Ruth Akali. Well, I started to I thought of starting the presentation with a more general introduction to galaxy clusters, but as it has been covered in some other fashion, I'll just skip this general introduction and directly get to the introduction of life cycle of a radio galaxy. We know that radio loud AGNs release energy via jets while undergoing a series of episodic core phases. A radio loud population can be evolutionarily segregated into a newly born radio source, the GPS and CSS source, or it can be a galaxy in an active phase like FR1 or FR2. Or it can be a phase where the core activity has just stopped and the overpressured jet blobs enter a phase of self-evolution under the and is called the remnant phase. The remnant phase forms a very important phase of IGM. Given enough time, these jet blobs will lose energy through synchrotron, inverse Compton, and adiabatic processes, rendering them to be radio invisible. These radio invisible pockets of plasma are then called radio ghost. The detection of radio ghost is difficult, but if these radio ghosts are caught up in a disturbance, it might re-energize the electron population and make them radio visible again. And these radio visible disturbed radio ghosts are then called radio phoenix. Uh, okay. So, yeah. Here we see an example of radio phoenix in Abell 4038. The structure is irregular and has highly axial morphology. Radio phoenix are filamentary sources characterized with a steep spectrum with a spectral index of less than -1.5. The precursor to these sources are lobes of radio galaxies, which have become radio dead after their central AGN has turned off. When these lobes are dragged into cluster disturbances originating from mergers or other turbulent processes, they undergo adiabatic compression, during which the electron gain internal energy, consequently making these sources radio visible. There are a combined of 14 known radio phoenix and phoenix candidates so far, out of which two have been modeled, and one can find the list of the same through the given links. Finally, the takeaway point is radio galaxy remnant forms an important component of IGN. And as we know that cluster merger is itself a continuous and energetic process which drives shock wave in the environment, this gives rise to shock compressed rebirth of radio galaxy remnants, making Radio Phoenix an important tracer of turbulent activities in the cluster. An intuitive model was presented by Enslin and Gopal Krishna in 2001, describing the journey of a jet lobe which disappears and then revives as a radio phoenix. Let us look into an outline of the model. Initially, we have a double-lobed radio galaxy. The core is actively pushing plasma population in the lobes of the galaxy. A typical lifetime of core activity would be around 15 mega year, after which the core turns off. Once the core activity stops, the overpressured lobes go into a self-evolving phase where it undergoes an adiabatic type expansion. This expansion continues till the lobe reaches a state of pressure equilibrium with the outside environment. By the time the equilibrium is reached, if enough time has already passed, the lobe may not have stayed radio visible anymore. This phase is called the lurking phase. When this lurking radio population gets dragged into a shock, either from merger activity or accretion from filaments of cosmic web, then the lobe gets shocked by the outside pressure jump. The pressure jump in the outside environment adiabatically compresses the plasma population, and the work done during this compression increases the internal energy of the system, and in this process, the electrons gain energy. This phase is called the flashing phase. This plasma compression continues up to a point till which pressure equilibrium between plasma and the post-shock medium is established, and again the compression stops. Eventually, as a result of heavy radiation losses, the radio emission also fades away. This phase is called the fading phase. Well, I'll not go into the mathematical details of the model, but I can say this. Through this model, given the information of previous phases of the source, we can predict the flux density of the source as a function of frequency for a current phase. But we do not know the history of the model, history of the source. So what we choose to do is approach the problem in another way. Given the spectra observed today, we explore a plausible parameter space through fitting today's spectra and then come up with a history regarding the different phases that the source has already been through. Here, I have provided a table of parameters we explored. The first two columns refer to the time parameters associated with various phases in the life cycle of the jet lobe. The Ci minus I is the compression ratio, and the Bi's are the expansion rates during each phase. The yellow ones is what we try to fit, and for the rest other parameters, we have a physical basis for their values. In order to obtain a plausible set of parameters, I wrote a Python code which compares observationally obtained flux spectra to theoretically obtained spectra. When given an input of physical parameters and a guess phase, that is a phase where we think the source is in, the code searches in a parameter space for these yellow colored parameters. This search is continued till a best representation of the observed flux is found. Having dealt with understanding the intuition behind the adiabatic compression model, let us walk directly into the application of this code on our target source Abell 1914. Now, Abell 1914 is a massive galaxy cluster located at redshift of 0.168. Botian et al. In 2018 had found surface brightness and temperature jumps in the system. Mandal et al. In 2018 classified the radio sources in Abell 1914 as a steep spectrum radio source, which is our Phoenix candidate, and a radio halo. The Phoenix candidate has an irregular and filamentary morphology and was observed to have a spectral index of -2. It showed a curvature in the spectrum. But how do we explain such a source? Conventionally, the electron population is understood to be reaccelerated by Fermi mechanisms. The cluster merger drives shock into the environment, which accelerates the electron population. But as the source shows a steep spectra and as spectral curvature is observed for the source, shock acceleration is ruled out. This, along with filamentary morphology of the source, makes this source a strong case that probably the source is a radio phoenix and has evolved through adiabatic compression model. So what we do next is use the spectral information of the source we obtained through observations, assume a guess phase depending on the morphology of the source, and fit the luminosity mathematical function from the model. This process takes us to the result of the fit. Let's see. So the black circles here are the observational data from studies through LOFA, GMRT, and VLA observations. And here I show two plots, one for fitting the flashing phase and the other one for fitting the fading phase. Each plot shows spectra for previous phases as associated with the adiabatic compression model, assuming a current phase of the radio source. We see that while the theoretical predictions for the fading phase, the given by the orange line here, falls steeply than the gigahertz observation data points. If the current phase of the Phoenix candidate is a flashing one, then it provides a much better fit. The beauty of this mechanism is that it not only tells us about the current phase, it also provides the history of spectral signatures of this source. Here we observe the flat spectra of the injection phase of the precursor radio population that has given rise to this radio phoenix. And also we can see the information about the other phases. Finally, Here is the list of parameters that resulted in this flashing phase curve. But how can we believe this set of parameters? Ideally, if we want to fit for flashing phase, we have current X-ray observations, we can obtain pressure jumps from X-ray data, and this pressure jumps would give us compression ratio. Once we have a compression ratio, we can have better constraint on the time scales. But as the X-ray observations were not deep enough to find a shock at this location, we move forward and approach the problem in a reverse fashion. We find a Mach number for the shock, which can result such a set of parameters. For this set, we have obtained a Mach number of 1.48. Now, we can say that if we went forward and re-observed the source in X-ray deep enough and found a shock of this Mach number, then this will confirm that the model is able to explain the radio emission of this source. So finally, we tried to understand a possible mechanism that gives rise to radio phoenix in Abell 1914. I applied and tested the model of adiabatic compression, found that indeed the model can explain the origin of the source qualitatively. I also put a value to the shock number that could have caused this emission. And if X-ray searches result the same, this will lead to a true confirmation of the model. In the future, we would like to have deeper X-ray observations of Abell 1914, which can give a better constraint on the fit parameter space. And we'll try to apply adiabatic compression model to more Phoenix candidates, which will tell us if there is an unmodeled physical phenomena associated with the process. Further, statistical study of Phoenix candidates with respect to the shock strength will also help us to understand if there is a lower limit to the shock strength that passively energizes the sources. With this, I would like to conclude, and I'll be happy to take any questions.